Hi everyone. So, we will continue our lecture on surface area measurement. In the last lecture, we were discussing about the BET theory, right. So, we are wondering there are a lot of isotherms which cannot be explained based on Langmuir theory, right. So, BET in Brunner, Emmett, Taylor, they came up with this relation where for an example, if you see in the plot, this type of isotherm type 2 isotherm can be explained. So, this is the relationship between Va over Vm, where Va is the amount of gas adsorbed at pressure P over Vm is the amount of gas needed to cover with the monolayer, right. So, we are when you plot Va over Vm against P over P0, which is the partial gas pressure, you get this kind of response, right. So, it kind of explains the type 2 isotherm in this case, and based on the value of C, you may get different shapes. Now, we were interested, we wanted to know how can we use this theory, right, to calculate the surface area. Also pay attention in this plot, this 1, right. So, V over Vm, when that ratio is 1, that means the gas adsorbed is equals amount of gas needed to cover surface with mono layer. So, same relationship can be written in a linear form, right, same thing. So, here what you see, again yesterday we discussed, suppose you consider this as a y, right, you are changing pressure, you are measuring volume, right. Also here is a P over P0, that is a partial gas pressure. This is slope for an example and this is intercept, right. This is the linear form, y equals to Sx plus I, right. So, when you plot y versus x, you will find this straight line, and where it meets the y axis, that is a intercept, and slope of that will give you this C minus 1 over Vm over C. So, if you know these, you can easily calculate the constant C, also you can calculate Vm. Is it clear? Yesterday we discussed that, right. And you notice the constant C depends on the energy of adsorption. E1 is energy of adsorption of ith layer. So, in this case first layer, okay, and LEL is like second layer onwards, right. Second layer, the energy of adsorption for second layer, third layer can be written as EL. So, this C constant depends on the difference between the energy of adsorption for first layer and lth layer, right. Okay. So, now the question comes, how do we calculate surface area, right. So, determination of surface area lies on premise that, so you have a surface, right. What we are assuming here, when we say the monolayer formation is complete, that means we have one layer thick, mono layer, mono is 1, right, one layer. Suppose you know that, you know the volume of gas adsorbed, right, when the mono layer just completes. If you look at the same thing in the plan, you may have a surface like idealized surface and you have these molecules, right, and you have only one layer. This we are looking from the top. So, how can we calculate that to find surface area? And you know this is a surface, right, this layer is on the surface, it is adsorbed on the layer. So, once we know the volume Vm, right, already we saw in the last slide, we can calculate the moles, right, Vm over V0, V0 is the molar volume of gas. Once you know the moles, we can calculate how many molecules will there be. 1 mole will have 6.023 times 10 to the power 23 molecules, right, that is a Avogadro constant. Once you know how many molecules are there, you can calculate the area by multiplying it by area of one molecule, that is the idea. So, we know the volume, right, we know volume of gas adsorbed, we have to find how many moles are there, that we can do by dividing it by V0. Once you know that, we have to now find how many molecules are there. That you can do by multiplying it with by Na, and finally you multiply it by An. An is the projected area. So, for example, this is a molecule, the area can be the projected area, right. You have a molecule sitting on a surface, right. So, the projected area on that surface will give you this value An. So, for nitrogen in case, this comes to around 16.2 times 10 to the power minus 20 square meter square. Okay. That will change if you are changing the gas. Sometimes people use argon, krypton, so that An will change, right. So, here you have a way to find surface area through BET, right. So, what do you need? You need to calculate Vm, and then you can calculate number of moles, multiply it with Avogadro constant, and then multiply it with An. Clear? So, that is what gives us the surface area. Okay. So, how do we select adsorbate? The question comes like, what should be the criteria for selecting adsorbate or gas which we use, right. So, currently nitrogen is used, right. It is widely accepted as a standard adsorbate because of its some unique properties. Which are those? There is no chemical reactivity with the surface. It should not chemically react with the surface, that is obvious, right. Low and well defined cross section area at its boiling point, right. It should have a low and well defined cross section area. No polarity, that will give you no lateral interaction. We want to make sure there is no lateral interaction between molecules. Should be widely available, right. And current adsorption equipment can measure absolute area as low as 1 square meter using nitrogen. That is the limitation as far as current adsorption equipments are concerned. But if you want to go below that, either way. So, if you want to measure surface area below 1 square meter, then either you have to increase the quantity of powder, so that net your surface area increases if possible. Otherwise, you will have to use other adsorbates like krypton, argon with lower saturation pressure than N2. So, there are ways you can use other adsorbates to measure lower surface areas. So, very important is how to prepare sample for this, right. So, first of all, we have already talked about stopping hydration, right. How do we stop hydration? There are ways, and you have to follow a way which can preserve the microstructure. Preserve microstructure is key, as drying method may affect it. When you dry things, it will affect your microstructure. If your microstructure changes, it will change your surface properties, right. So, solvent exchange using isopropanol is preferred, but it may lead to dehydration of eternite on long exposure. That is the downside of it. For long exposure, eternite may get dehydrated. So, what is recommended? Short contact with cooled isopropanol. Cool means 5 degrees Celsius temperature has been shown to preserve eternite crystalline structure. Okay. So, once you stop hydration and you have a sample, before you do this adsorption test, you have to degas sample. Degassing is you have to remove any gas which is physically adsorbed on the surface, okay, before making adsorption measurements. So, it is normally done under nitrogen flow. Degassing means you do it under nitrogen flow or vacuum at high temperature to accelerate the process, okay, because if you do not use high temperature, it might take long time, but you also do not want to use too high temperature, as we will see. So, what is the influence of degassing temperature, right, on surface area measured by BET, right. So, here we see this figure shows the influence of degassing conditions. On x axis you have a temperature. So, you see 40 degree, 60 degree, 100 degree, right. What is evident? As you are increasing the degassing temperature, your surface area also is increasing, right. So, that is affecting, right. So, degassing at 40 degree Celsius under nitrogen flow for 16 hours has been shown to be an optimal degassing method. If you do it for longer, then it may affect your microstructure, and that will reflect in your measurement, right. See here, you see like degassing, so this red one is here degas like 16 hours of degassing in vacuum. The blue one is degassing 16 hours in nitrogen flow. So, pretty much close, but as you now if you do it 24 hours 14 degree Celsius vacuum, right, as you are increasing the time, you see it is affecting your surface area. That is just at 40 degree Celsius only, right, if you increase the time. But if you increase now the temperature also, that significantly increases your surface area. The point is, it is good to maintain low temperatures, not too high temperatures, because that if you go for high temperature, although it will accelerate your degassing, but it will affect your microstructure, which you do not want. Okay, so here are some specific guidelines if you want to use nitrogen adsorption test. First of all, adsorbate gas, right. So, nitrogen with purity of at least 99.9% must be used, okay, very highly pure nitrogen. Sample weight is always controlled before and after degassing as well as after adsorption measurements. Sample weight should provide at least absolute surface area equal or higher than 1 square meter, right. For nitrogen we are talking about. If you have to go below 1 square meter, then you may have to use other adsorbates like krypton, argon, right. Sample tube cell should be immersed to a depth of at least 5 centimeter below the liquid nitrogen level, because you are putting your sample in nitrogen environment. So, it should be at least 50 millimeter below the liquid level. Isothermal jacket should be used, right, to maintain the constant temperature in sample tube immersed in endeavor while liquid nitrogen evaporates. Now, stopping of hydration, right, and degassing conditions. So, this is for the anhydrous material. If you analyze cement, fly ash, SCM for an example, anhydrous cementitious material. So, for cementitious material containing gypsum, mild degassing condition must be applied to preserve gypsum microstructure and composition. You know that cement contains gypsum. So, if you use high temperature, it will lead to dehydration of gypsum. So, you have to make sure that you are using mild degassing conditions. Specifically, degassing at 40 degree Celsius again under nitrogen flow for 16 hours is recommended. That does not affect. That is what people have seen. Higher temperatures or vacuum treatment would prompt gypsum dehydration involving significant structural changes. If you use higher temperature, it will lead to dehydration of gypsum and involve significant structural changes that will be reflected in your surface area measurements. Clinker or supplementary cementitious materials, clinker does not have any gypsum, right, and supplementary cementitious materials such as slag can be degassed at relatively high temperature. So, where you think there is no effect on constituents, you can use higher temperature, right, for 1 hour in this case without modifying its microstructure. So, it depends on the material, what kind of material you want to analyze. So, typically how do we report specific surface area? We report equipment used, very important. When you do work, you have to report which instrument did you use. Method of stopping hydration, it is very important to also mention which method did you use to stop hydration, because that is going to have impact on your measurements. Degassing conditions, temperature, pressure, if vacuum or nitrogen flow was used, and time, for how long, what were the conditions of degassing, right, these are very important. And also finally, it should include standard deviation from repeated measurements. These are typically things which we report when we carry out surface area measurement using PET. Okay. Now, you have looked at various techniques. We saw we can determine surface area using Blaine, air permeability, also we can determine using laser diffraction and BET. Now, it is good to compare, right. So, here we have a comparison between Blaine versus BET, right. So, usually specific surface area determined by BET is higher than Blaine, okay. We talked about it, because as nitrogen can access cracks, crevices and pores that Blaine test is not able to distinguish. So, nitrogen has that capability to go inside cracks, crevices, right, and pores which are not considered in Blaine test. So, usually the values you get of surface area through BET will be higher than Blaine. So, you see here, so this is the y axis, you have a Blaine fineness, right, x axis you have BET. So, typical values, suppose this one is close to 500 in this case, and here So, you can see this is a specific surface area of clinker, cement, fly ash and slag from this paper, right. So, if you look at the specific surface area determined for clinker, cement, fly ash, slag, you see it is a general trend, right. So, BET values are higher. So, that is good to know, right. Also, air permeability test does not give reliable area values for fly ash powders, as it is not able to detect the internal surface of unburnt carbon particles. So, you a lot of times have unburnt carbon in fly ash. So, that the internal surface we cannot measure using air permeability. Again, here it is a table which kind of gives you an idea about the comparison. Here we are comparing BET, laser diffraction and Blaine, right, all three measurements, right. So, this was done, you can refer to this paper if you want to know more. The test was done on two types of fly ashes, two types of slags and silica fume, right. So, you again see BET values are higher than Blaine and laser diffraction. So, that you should know. Why? Also we know that because other tests do not consider the porosity, roughness of particles, right. So, here we can, as long as nitrogen molecules can access cracks, get into the pores, right. So, as long as they can go inside, we will be able to determine the surface area, right. That is the thing you need to take away from this slide, right. And also notice that laser diffraction, right, it is very critical to the optical model you use. We do not, lot of times we do not pay attention. So, here you get the same two different values. I put the star is like two different optical models. What does that mean? Different values of n and k. Optical values means different values of n and k. N is refractive index of your particle, k is absorption coefficient. So, based on different, in this case I think n value was same, but k was changed. So, it gives you different numbers. So, very important when you do these tests, you have to know the limitations, assumptions, what optical model you chose. So, here that is why you see two different values. Okay. Okay, now we will look into applications of this BET surface area to construction materials, right. Now, we know that we can measure surface area using different techniques, but in this case we will look into the application of BET surface area, which is commonly used and gives you very close to true surface area. So, here is, you see, surface area of cement paste, right. How does it change? With hydration. We know that cement hydrates, you have formation of calcium silicate hydrate, right, with time. So, degree of hydration increases with time, right. So, what is the influence of degree of hydration? So, here you see on y axis you have a surface area, plotted x axis you have a degree of hydration. So, what you see an increase as the hydration progresses, as the degree of hydration increases, you see increase in surface area. Why? Because increase in degree of hydration will lead to increase in the amount of calcium silicate hydrate, which is the gel, and that means you form more gel pores. So, you are forming more gel pores as the degree of hydration increasing. So, increasing the surface area. Okay. Here is the data from different water cement ratio. Here you see combined 0.35, 0.45, 0.55 and put together, there is a nice correlation between surface area and degree of hydration. Okay. So, let us look at the influence of gypsum dehydration. We talked about that at higher temperature gypsum may dehydrate. So, how does that affect the surface area measurements? So, here you see, so higher temperature during degassing leads to dehydration of gypsum. Okay. So, here you see two, one is 40 degrees Celsius, one is 100 degrees Celsius. Measurements were done at two different temperatures, right. 40 degrees Celsius degassing, before carrying out adsorption test, you have to degas your sample. You have to make sure there is no gas adsorbed on your in your sample. And also you see different data points here. One is the model cement, one is one was model cement done in nitrogen flow, model cement done degassed in vacuum. One is clinker, right, clinker. So, you see, first of all, clinker does not get affected. Clinker is here, let us see. Sorry. So, this is a clinker, right. So, clinker does not get affected, make sure it is fine because there is no gypsum in the case. But if you look at this cement which has gypsum, you see increase. So, that clearly tells you gypsum is getting affected by your degassing temperature. Also, if you look at this plot here, here we have phase fraction by Rietveld. You can do quantitative X-ray diffraction, right. We discussed that in X-ray diffraction lecture. You can determine, because these are crystalline phases, you can determine how much of it is in the cement, right. So, you see that initially you have a, so here you see gypsum, hemihydrate and hydride, right. You have a significant gypsum, right, in untreated reference, you know, it is cement. 40 degrees Celsius, there is not much change, right. Pay attention to this blue. What is happening when you increase to 60 degrees Celsius? You see reduction in gypsum, an increase in hemihydrate. So, you see the dehydration of gypsum is taking place. Finally, at 100 degrees Celsius, most of your gypsum is gone. You have anhydrite. So, it tells you that as you increasing the temperature, your it leads to dehydration of gypsum, and that will get reflected in the measurements. So, it depends. So, kind of material, if you are analyzing clinker, it is fine maybe to go to higher temperature for degassing, but if you are working with the cement, then it is important to restrict the degassing temperature to 40 degrees Celsius. Okay. Okay. Also, we can determine specific surface area of Ettringite, right. What happens when you use different sample preparations, because Ettringite phase is very sensitive, right. So, to temperature. So, here also again you see, as long as temperature is below 40 degree Celsius, temperature means degassing temperature we are talking about. As long as it is below 40 degrees Celsius, you do not see much change, but as you increase the temperature to 60, 80, 100, you see increase in BET surface area. Again, this Ettringite structure gets affected when degassing temperature is higher than 40 degrees Celsius, leading to higher specific area. So, these are the things you have to be aware of. Suppose you have a cement where you expect Ettringite, right. Now, if you want to determine the surface area, right, then you have to restrict the temperature to 40 degrees C. If you go higher, then it will affect your structure, that will get reflected in your surface area measurements. Here we see the influence of PCE, it is kind of a superplasticizer. We know that why do we use superplasticizers? Yeah, to increase the workability. So, but the PCE is a polycarboxylate ether, right. Superplasticizer on again specific surface area of Ettringite. What is the effect of this type of superplast? What do you see here? So, on the left plot we have again surface area plotted on y axis, time, right. So, you see without PCE in the sample when you do not have any PCE. So, this is the trend, right. And then you add PCE 0.05% weight, 0.1% weight, 0.15, you see increase, clear, right, with the time. And here they use the different type of, here is C20 and there is a C38. This is just difference in the polycarboxylate ether like PCE superplasticizer. Again you see similar trend, right. So, what does it tell you? Addition of PCE in this case led to increase in specific surface area of Ettringite. So, these kind of things can be monitored using nitrogen adsorption, right. So, if you want to look at the interaction, what happens to surface area, right, it tells you definitely that something is happening. Anyway, we are not going in detail, like for details you can refer to the paper here, right, what is the cause, what is happening, but these are the changes which you can capture using nitrogen adsorption test. Okay. Also, we can use nitrogen adsorption test to determine specific surface area of clays, right. Here in this paper again very detailed study was done on different types of clays. See here Montmorillonite clay, right, illite, different types of clays, right. Mineralogy is given and you can determine specific surface areas, right, and you get very good reasonable values, right, with very low standard deviation. So, idea is this can be also used to study clays, right. Here different clays were studied, you can see the values, right. In some cases you have high values also like synthetic clays. See the difference is SY, this is synthetic, right. You see the values are higher, these are the synthetic clays, right. Yeah. So, you can use this nitrogen adsorption to determine the surface area of clays. So, in summary, what we have studied, what we learnt, see, these are the main points you should take away from this lecture. Two aspects, both particle size distribution and surface area are complementary, right. If you have a particle, if you have material which has very fine particle size distribution, that tells you it has higher surface area. So, these tests are complementary, right. So, how do you determine particle size distribution? Easy way to do determine is do sieving, right, commonly used, but sieving has its limitation, that is what we looked. If you have particles below 50 microns, it makes it difficult, it is not feasible, right. So, for coarser particles it will work, no issue. Another technique commonly used is laser diffraction, right. Again you have to remember the assumption, it assumes that the particle sizes are spherical, shapes are spherical, right. Requires knowledge of refractive and absorption indices of particle, very important, right. You need to know your material, like then only you will be able to get reasonable values. Also you need to avoid the over interpretation of PSD tails for non-spherical size particles, okay. Like we saw that, because if you have non-spherical size, it tends to broaden the distribution, right. So, too much over interpretation is not recommended, right. Dispersion conditions need to be optimized, right. If you have a particular dispersion method, dispersion is you have to make sure you are dispersing, you de-agglomerating your sample, right. If you have condition like for cement, that may not be directly applicable to SCMs, you will have to optimize this dispersion condition, like what is the frequency, what is the, like if you are doing sonication for an example, right. So, these dispersion conditions specifically need to be optimized for SCMs, okay. Then we looked into surface area measurements, three ways, right, how do you determine surface areas. Plane air permeability, again you have to remember the assumption there, so mono size spherical particles, right. So, for that you have to calibrate your apparatus, so empirical calibration is needed, okay. The value you get is lower than true surface area because of its limitation, right. Next one is laser diffraction, again assumption is spherical shape of particles, right. Here again there is no consideration for roughness and particle porosity, right. No calibration required, but in this case no calibration is required, like what you need for plane air permeability, right. And again the values are lower than true surface area, right. It has also its limitation, you are measuring volume, right, but does not know about the roughness of particles, porosity of particles, right, that is not taken into account. Finally, gas adsorption theory, there is no assumption regarding any particle shape and size, right, it gives you value very close to true surface area, okay. So, these are the main takeaway points from this lecture. With that, we will conclude this lecture. I will just point out again, most of the material was taken from this practical guide to microstructural analysis of cementitious material on this chapter on laser diffraction and gas adsorption techniques. Anyway, this textbook we have referred in this course. There are a lot of other papers like you can see and books where the material has come from, okay. So, that will conclude this lecture. So, in the next lectures, Professor Manu Santanam will be talking about microscopy, image analysis, spectroscopy and pores size determination using mercury intrusion porosimetry and also impedance techniques.